Hello, everyone, and welcome to the second Surface Ventures Mini-Symposium. Great to have you all with us. It'd be great if you could just say hi in the chat. Tell us where you're joining from today. My name is Dr. Sam McMaster. I'm the content manager here at Surface Ventures. We are a non-for-profit organization, and our mission is to provide world-class materials and surface science education for both academia and industry. Great to see some people are beginning to say hello in the chat. Thank you very much. We'll have multiple speakers for our mini symposium today. Okay, so we'll be all on fretting wear and fretting fatigue. We'll begin with Philip Shipway, talking about a physical framework to understand fretting wear, and we will proceed through the speakers as shown on the agenda just there. Many thanks to today's partner, Optimal Instruments. We'll have a presentation for Dr. Amanu Snyder of Optimal Instruments. Midway through our event, we'll be releasing poll questions and handouts from Optimal. As we go along, please type your questions into the chat, so we will answer each of the speakers' questions after their talk. They will be speaking for about 20 minutes, and then we'll have 5 minutes allotted for questions. Okay, so I'll be marking questions for the Q&A there, so please do type them in the chat. We're planning to go for just over 2 hours today, and we'll be sharing a link for attendance certificates later in the event. So now let us welcome our first speaker to the stage. There you go, Professor Philip Shipway from the University of Nottingham. Philip Shipway is the Cripps Professor of Engineering Materials at the University of Nottingham, where he's been a member of academic staff for over 30 years. Over the years, his research has addressed both mechanisms of wear and development of wear-resistant materials. Along with Ian Hutchings, he's co-author of the second edition of the textbook, Tribology, Friction and Wear of Engineering Materials. And from 2013 to 2018, he was co-editor-in-chief of the journal Wear. Great to have you with us, Philip.
Nice to be here.
Excellent. Let me bring your slides up. There you go. Fantastic. Take it away.
Great. Well, it's very nice to see you all here this afternoon. It's the modern way of presenting. I think we'll do okay. But what I wanted to talk to you about this afternoon was a little bit less on a sort of, some new results, etc., but really something to do with a sort of fundamental understanding of the concept of fretting wear and what it is that controls that. So, as I said in my original, as it were, promise to you, we're going to be looking here at well, let me say first of all, I'm going to be focusing on work of metallic contacts in air. So fretting, people will fret, or we will see in service environments, fretting in all sorts of conditions. We see fretting in lubricants, where some of the issues to do with oxidation, etc., are quite different. We see fretting of non-metals. We see fretting actually of metals that are not prone to oxidation. But this is primarily I'm looking here primarily at steels. Most of our work has been conducted on steels. And I'm going to present a framework, but in reality, the framework that I'm going to present is also relevant. The understanding of it, because it's a basic physical framework, you can think about what is relevant for other situations. So, for example, that situation of fretting in a lubricant, what would be different, what would be the same to what we're looking at today? So I'm going to make some suggestions as the differences between sliding and fretting contacts. That's, we know that most of us know what a sliding contact looks like. Most of us would think we would know what a fretting contact looks like. But then there's that sort of middle ground of are we sure, would we describe this as sliding or fretting? I'm going to offer some thoughts around that, although I'm afraid I'm not going to say, I've got a new definition of what that is. What I am going to do is to introduce you to the basic processes, the basic physical processes involved in the wear of fretting contacts, particularly, as I say, the fretting wear of metals. And this is all about wear. I'm not going to be looking at fatigue at all within my presentation. And then, you can think about all that. There's lots of what you might call test variables or parameters. Many of you are interested in the area of fretting will probably know of a particular paper that talks about, are there 50 parameters that control fretting wear? And the answer is, yeah, there's an awful lot of things that if you change them, they seem to have some effect. And I think a physical framework allows us to get some idea of what are these various parameters that we might say test variables doing to the physical processes they're operating. I'm just going to touch on a couple of those. I can't go through all of those in a short talk like this, but hopefully you'll see the value of this approach. Okay, so we start off with that sort of sense of fretting. What is fretting? We all probably know that fretting is small amplitude sliding, and many of you will recognize that chart in the bottom right-hand corner of this particular slide, which comes from work of Vingsbo and Soderberg in 1998, where they said, look, this is how the wear rate varies with the displacement amplitude. And they said, right, down at the left-hand side of that, it's stuck. Then it moves through a mixed stick-slip kind of regime where there is fretting probably at the edge of the contact. Then it moves through what they term gross slip, and that is where the whole contact is moving, but it's probably not moving very far. And they've given their displacement amplitudes there, as you can see. And they went up to about 300 micrometers, and they said, look, once it goes above about 300 microns, then we're going to call that sliding. And they said, actually, one of the key bits for them was that they saw within that, that when it went into sliding wear, what happened at that point was that the wear rate pretty much remained constant, the sort of Archard style wear rate that they were measuring there. So that's where this number of 300 micrometers comes from. But I would suggest that a key feature of a fretting contact is that it remains closed during the cycle. And what I mean by closed is, I mean that one or other of the members remains entirely, a part of the original contact remains entirely covered. It doesn't get open to the atmosphere. And when we talk about open to the atmosphere, we mean, that there's direct oxide contact with that surface, but it's probably also something to do with the way in which the debris is flushed out of the contact. So that idea of a closed contact. So of those two images on the top surface, at the top of my slide here on the right-hand side, the right-hand one of those I would refer to, that remains a closed contact, whereas the one on the left-hand side of those two images, where delta is larger than L, the contact width, then that is what we might refer to as an open contact. And in fretting, I would suggest that there's always some level of a closed contact. That probably tells us that therefore this 300 micrometers, you might be sitting there wondering, what about this 300 micrometers? Of course, if your contact size is very small, then actually you've still got to have a close contact. So when people talk about small scale, very, very small scale sliding, but potentially with very, very small contacts as well, we need to think, is that really fretting or is that something else? When the contact is closed, as I say, we need to think of transport of media. And what I'm going to try and explain on this next slide, what I mean by that. We start off, look at those three images along the top here. We start off on the left-hand side with our original contact. This is not the full contact. This might be the contact edge. It doesn't really matter. But we've got some kind of oscillation. We've got this oscillation by delta, the slip amplitude there. And we start off with a metal-on-metal contact. What we all know is that actually after a period of time that we end up with oxide coming out of the contact. People refer to it, if you read those very old papers, people refer to it as looking like cocoa powder. It's very, very fine, dark brown debris because it's iron oxide, Fe2O3 typically. So what is going on to allow that to happen? Remember, this has to happen across the whole contact. You can't have nothing happening in the middle because in the end, then the contact would stifle. or the wear would stifle. And so what we need to have for that is that we need to have oxygen flowing in to the center, because we know that everything that comes out, pretty much in whatever conditions in these kinds of tests, we measure this. You can extract the debris and look at it, and there's a reference there at the bottom. And we see that the debris that comes out is oxide. It's not full of metal. It's full of oxide. And to allow that to happen, therefore, we need to be getting oxygen flowing into the contact and debris flowing out of the contact. And the reason I say that debris must be coming out is because what we also find is that the oxide thickness, if it does form, it tends to not grow very large. However long you leave the test for, we've run tests quite often out to 10 million cycles. And we find that a 5-micron debris bed will develop in maybe the first 100,000, and then it stays at about the same thickness forever. So we obviously reach some form of equilibrium within that system. Sometimes the oxide is like that. Sometimes the oxide is much thinner, patchy, you might describe it as. The right-hand side of my 3 images there. And we can still then be getting oxygen flow and debris flow out, but it might mean that either the debris is flowing out really rather quickly, it's very easy for the debris to flow out, or it might mean that the oxygen is struggling to get into the contact. And different things will mean, it's difficult to distinguish when you see a thin or patchy oxide with lots of metal in the contact. It's difficult to quite know what the difference is, but it at least provides us with some level of understanding through our framework. Okay, so on to the next slide, something that we call the rate determining process. We published a paper in 2021. It's the one where the reference is at the bottom left of the slide here. And the concept of a rate determining process wasn't new, although we spent some time in that paper really elucidating what it might be. But in fact, there's a rather nice diagram that when we published that paper, I've got to be honest, that I missed. In part because it isn't referred to very much within their paper. But there's a lovely paper by Siegfried Fouvry and Thomas Lišković, who is obviously has driven a lot of this work here with Surface Ventures. I think Thomas is online. So Thomas, just to say, yes, I have now worked out that the diagram that we're now using is originally from that paper. You didn't spend a lot of time in that paper talking about it, but it's a very nice diagram. I'm going to just try and very briefly talk you through what that diagram shows. It says in broad terms, if there are numerous things that have to happen, numerous processes that need to happen, all of them, for something to happen, in this case, wear to occur within fretting, then the overall process will happen at the slowest of the rates of things. You think of a flow in series as they have shown it in the diagram here on the right-hand side. And they talked about the rate of debris formation and the rate of debris ejection. And they said the critical word within their diagram is possible. In the second line down, it talks about the possible rate of debris formation. Yeah, sure, the debris could form quite quickly, but in reality, in the case that they're showing here, the flow of debris out of the contact was really quite limited, and therefore the overall kinetics were that of the flow of contact out. So a really nice understanding there. In the work that we then further developed, which was in 2021, we talked about that rate of debris formation. We broke that down into 2 stages. We said there's the rate of oxygen supply. So to get this debris to form, it's an oxide debris. There's the rate of the oxygen supply. There's the rate of wear and debris formation itself, what we might call the Archard term within the system. Archard, remember, Archard's work was all about sliding wear. So the idea of applying this to fretting is somewhat of a stretch anyway. So I don't want to sully Archard's name. Archard's work is obviously foundational to our understanding within this kind of area. But Archard was primarily talking about sliding. We're maybe misappropriately using, or we sometimes misappropriately use Archard within the area of fretting. So let's have a look at this next diagram. This is just simply the same sort of diagram, that Fouvry, Liskovich et al. Put together in 2023 and 2003 rather. And you can see the way that we've put this together here. So we've got our oxygen flow, we've got our debris formation, which we're suggesting in this particular example. Look at the left example there. We're suggesting that's large. And then we've got the debris egress, the debris loss from the contact. And we say that the wear rate that we observe in this case doesn't really matter what the wear and debris formation is. If that changes a little bit, it's not going to change anything because everything's controlled by the debris egress in this sort of area. Likewise with the oxygen flow. But what we will see is if we push the debris egress up, so as I've gone from the left-hand side to the right-hand side, I've assumed that we've left parameters the same that won't change the oxygen flow, they won't change the wear and debris formation, but they might change the debris egress. For example, we now know that actually things like the fretting amplitude is probably one of the key ones that does this. Doesn't change the other things, but will change this quite significantly. What we then see is that as we push the debris egress up, as it were, that part of the pipe gets bigger. Look at the figure on the bottom right there. As we push up the debris egress, the overall wear rate will increase as we move from the left-hand position to the right-hand position. The wear rate will increase until it's stifled, in this case, by oxygen flow. The debris egress has got big, and suddenly at a certain point, it stops being the rate determining process. So in this case, you can do what you like now with the debris egress. It can get bigger and bigger, and you won't see any change. And that's why in the bottom right corner, we've got the observed wear rate increasing with the maximum allowable debris egress rate, and then stifling because actually now it's controlled by the oxygen flow into the contact. So that's why sometimes we see rather odd effects within our systems, because we need to be thinking about all of those processes, which one is rate determining. Okay, so let's have a quick look at some other data. We won't spend very long on this. The key bit of the presentation, as it were, if you've followed me up to now, you've got the main bit. We did some work with cylinder on flat geometry. The work that I'm going to present, it's one of the things that as time has gone on, you realise that actually non-conforming contacts such as ball on flat and cylinder on flat are actually much more difficult than flat on flat contacts. And it's partly because we've now come to a position where we say, actually, we think one of the key things that controls wear rate in many tests is that of the contact size, the contact width. So as we've got it here, so if the image that I've got at the top is the way that we do our tests. We have a cylinder on a flat, and we move the cylinder perpendicular to the axis of the cylinder. We get a wear scar width, but that wear scar increases in size through the test. We know that the wear scar always takes the form of this, essentially what you might say is the segment of the circle, the prismatic segment of the circle is what we've managed to, we've shown that through tests like this. So I'm not going to really spend very long on that. You can go and have a look at that in some of our work that I've referenced. But what we did notice is that, well, we conducted tests with both cylinders with 6mm radius, so really quite small cylinders, and very large cylinder radii of 160mm. We used everything else the same though. And if Archard was relevant in that way, so Archard in very broad terms, Archard or a derivative of Archard, the energy version of Archard, says that the wear volume will be proportional to the energy dissipated through in the test. And if that was true, it shouldn't make any difference what size your cylinder is. And in fact, the data that we've presented here in the middle diagram, that's with a 160mm test and a cylinder rather, and a 6mm cylinder. They're very different. But what we proposed, based on some earlier work from the 1980s, was that actually we proposed that the wear rate, dV by dE, the wear rate, was proportional to 1 upon the wear scar size. So the inverse of the wear scar size. The justification for that is that the debris finds it more difficult to get out. The debris finds it more difficult to get out the bigger the scar is. So small scar, debris escapes easily. Big scar, debris finds it very difficult to get out. We proposed then a relationship based on that, and there aren't fitting constants. That relationship that I've got there on the figure that says, or on the slide that says V is equal to A R to the minus 0.25 E to the 0.75. That isn't fitting data. That's simply a geometrical expression, and you can go to the paper to see how we pulled those sorts of things out. And what we were able to do, sorry, let me flick back. What we were able to do then was to show with the figure on the right-hand side, when we plotted now the wear volume versus R to the minus 0.25, E to the 0.75, all of the data fell onto a straight line. And we did that with 6mm cylinders, 15mm cylinders, 80mm cylinders, and 160mm cylinders. And we've also applied it to work of others where they've done work on sphere on flat, and we've demonstrated through a variety of places that this holds good, this concept that the wear depends pretty critically on the size of the contacts. So that means that just applying ArcChart is not appropriate. I'm just going to very quickly touch also on some work on frequency, because again, frequency, ArcChart shouldn't really make any difference. Frequency shouldn't make, if we adopt an ArcChart approach, that one that says the volume is proportional to the energy, then the frequency shouldn't make any difference. But there was work that was published by Fouvre et al. In 2017 on the on the left-hand figure there, where they said that the wear volume under a certain set of conditions really fell off very, very quickly as they increased the frequency from about 0.5 hertz up to 5 hertz. If you plot that in an ArcChart sort of style, as it were, that's the middle figure there, the wear volume versus the energy dissipated. The energy was about the same in all of those figures. Not surprising. They were doing exactly the same test except for the frequency. And they saw this stack up of a five-fold difference in the wear volume. What we did is actually we looked at the wear rate. So we simply took that figure, that middle figure, and divided it by time. So you end up then with a wear rate, and if you divide one by time, you've got to do the other one by time. You then have power dissipated. And what we found then was that the wear rate stifled. As we increased the power, the wear rate stifled. And so we ended up with that horizontal line across the top. And we said that was a time-based wear rate, not a per joule of energy. This is now time-based. And we said that we believe that is to do with oxygen ingress, that was a limited rate to do with how fast the oxygen could get into the contact. So I realize I've gone through those two examples really rather quickly, but the overall concepts are the ones that I really wanted to get over to you. This sense of we need to think about the physical processes, and that thinking about the physical processes that control this allow us to start understanding why things like frequency and contact size might affect things like fretting. Fretting, I believe, is far more complex than sliding wear. It's a lot more interesting to study. And that definition of when is it fretting and when is it sliding, well, it's still, you might say it's still open to debate, but perhaps it can be defined as a situation where either oxygen transport or debris transport are the rate determining process. I've overrun very slightly there. Sam, I apologize for that, but I'm happy to take questions.
Not a problem, Phil. Don't worry about it. I saw you were getting quite close to the end of your talk, so I didn't want to interrupt you. Okay, so we have time for a question or two. If anyone in the chat would like to type something in, we can address that. But for now, just to perhaps a little bit of a silly observation, but since we're talking about the effect of oxygen transport into contact, are you aware of any work, or perhaps have done any work of trying to conduct some of these fretting experiments in vacuum to then see the component of oxidative wear completely removed? No?
So we haven't. Well, we have done some work. We've done some work in Nottingham in argon, but there's quite a long history of people doing work in the area of tests in vacuum. And what one tends to find is that the wear rates are much smaller, but obviously it's a completely different mechanism. So it comes back to that bit that when I introduced at the beginning, said, look, I'm talking about things that are happening in air. If you tend to do it in vacuum, you tend to end up with a lot more subsurface damage. So what people talk of the tribologically transformed zone, because you haven't got the oxide is very protective. We did some work on just elevated temperature fretting, and what you find then is the oxide forms a glaze, and that protects the surface. So the oxide is really important. If you are working in vacuum, it will be quite different, and it's likely to be it degrades, it forms a lot more subsurface damage. But actually what you also find is that the wear rates are much lower. It's very difficult for debris transport, and sometimes the wear rates look tiny and you think, oh well, this isn't too bad, and then you look subsurface and there's cracks everywhere. So then the fretting fatigue people then become terribly upset, and rightly so, you know. So it tends to lead towards a much more damaged structure within the metal itself.
Yeah. Okay, that's very interesting. Thank you. It looks like we don't have any questions from the audience right now, so I'd just like to invite, you know, if anyone in the audience would like to ask Professor Shipley a question, please do type that in the chat. I hope you'll be staying with us for some more of the event and could could perhaps here we go, one quick one here, which will bring out from Vignesh Kumar, so who asks, Professor, oxidation plays a vital role in fretting wear, and it tends to lead to material cracks. Is that correct?
So I'm not. When you said it tends to the material crack, I guess if you're asking, does the oxidation in fretting result in cracking of the material? I would say not necessarily. So the oxide is formed as the materials fret against each other. It forms because you expose new surfaces. That surface, if there's enough oxygen getting in there, the surfaces, that metallic surface will oxidize. One thing that I think is still not entirely clear is does the metal particle come off the surface and then get oxidized, or does the surface get oxidized and then be removed as a metal particle? You might say, you know, who really cares which way around it is? But you know, it's one of those questions that I think we need to answer. But the oxide generally is a protective oxide, or it provides some protection to the surface. Although as it leaves the contact, it does it does provide a good mechanism for getting material out. So as I said a moment ago when Sam asked that question, we tend to find that if we have little oxidation, we tend to get material cracking. Quite often, if you've got a lot of oxidation occurring in a fretting contact, the level of subsurface damage can be quite low. And one of the questions that you've got to ask is, are we more worried about the wear, about the loss of, essentially loss of dimension, which might lead to problems in a structure, or are we worried about subsurface damage, which tends to promote, well, from the look, you would look at it and you'd say, well, this is going to be a fatigue issue. So one needs to say, what are the big issues here? But I wouldn't say that necessarily oxidation or oxide itself tends to form cracks within the structure.
Okay, that's great. Thank you. So with that, I think we'll have to move on to the next speaker. I did notice there's a question in the chat there from Ali. I don't know whether if you are able to type a response to him, but just to make you aware of that. Thank you very much.
I'll see what I can do.
That's great. And thank you so much for your talk.
All right. Thank you.
Okay, so now we'll be welcoming our next speaker to the stage in a moment, Professor Alex Araujo from the University of Brasilia. As a full professor in the Department of Mechanical Engineering at the University of Brasilia, his research interests involve the modeling, simulation, and experimental characterization of wear and fatigue, multi-axial fatigue, fracture mechanics, and contact mechanics. Alex got his PhD in engineering sciences from the University of Oxford in 2000, and he's a founding member of the Committee of Fatigue and Fracture Mechanics of the Brazilian Society of Mechanical Sciences and an affiliated member of the Brazilian Academy of Sciences. He's published more than 120 articles in international journals, holds a H-index of 28, and has supervised some tens of PhD and MSc students. Excuse me. So with that, let us welcome Alex to the stage. Let me bring his slides up, and we'll begin in a moment. There we go. Welcome.
Good morning, sir. Can you hear me well?
Yes, I can hear you. Fantastic. Thank you very much for joining.
For you. Could I upload my own slides, because I think there is a move that I would like to show. Is it possible?
Oh yes, we can do that quickly. So yep, let me bring these up. There is the start sharing screen button. For everyone in the audience, give us one moment. We will just set this up. So with screen sharing, if you could please share your whole monitor, and then you can put PowerPoint just into presentation mode, and that will capture everything.
Yeah, I think we are.
Okay, great.
Is it showing?
Give it one moment. It should come up. Ah, there we go. Perfect.
It's okay?
Yep. Great.
Can you start?
Yes, please do. Thank you.
Okay. So thanks a lot, Sam, Thomas, for the organization of this very interesting activity. Thank you all for coming and well, using your time to stay with us to talk a little bit about threatening fatigue. Today, I'm going to talk about threatening fatigue of overhead conductors. The idea is to introduce some basics of the threatening phenomenon on overhead conductors, which is caused by aeolian vibration. And also I will introduce some reduced scale strategies to estimate the life of these components that we have developed over here in the University of Brasilia. So some basics of threatening. Philip has already given us a very nice introduction to the problem, so I will be quick here. So the term threatening denotes a small relative displacement between contacting surfaces. Usually, I will use this cylinder against plane contact configuration to talk a little bit more about this. So usually you have, well, first you need to press together the two components to create a contact surface. And usually you have this tangential load, which is parallel to the surface in this case. And if this load is smaller than the limit to cause slip given by the Monton's law, you will see the development of slip zones within the contact, where you will see also some loss of material and a small surface damage. Okay, on the right here, I make a comparison between the threatening fatigue problem and the fatigue problem in knots, because they are very similar, and this can allow us to obtain some strategies that we usually consider for the notch problem inside the threatening fatigue problem. Okay, so what you can see in the first picture is the contact of a cylinder against a plane, and what will happen is that we have a strong stress concentration close to the contact. These high stresses, they decay very rapidly as you come away from the surface, so you face a strong stress gradient in these threatening problems. This is very similar to what occurs in notch problems, okay? Also, you will face a high stress concentration at the knot tip, and the stresses will decay very quickly as you go away from the notch. Also, in both problems, a multiaxial state of stress will develop as you move inside the specimen, okay? So in this table, we summarize this comparison where you can see that in the fretting and in the notch problem, fatigue problem, you have a number of similarities. You have stress concentration in both. You have stress gradient present in both problems. You have multiaxial stresses present in both problems. But in the notch fatigue problem, you do not have the presence of surface wear. Okay? Well, and in conductors, how the fretting problem occurs in conductors. So here in the left, I have the scheme of a suspension clamp together with the conductor. These suspension clamps, they are attached to the towers, okay? So when the wind blows perpendicularly to the cable, you will see the movement up and down of the cable due to the formation of a vortex shedding, okay? So you have the vortices forming around the conductor, and then you will see this sort of up and down movement that will generate two problems. First, you have cyclic stresses, cyclic bending stresses in the wires of the conductors. Usually these conductors have some layers, as this one that I'm showing this slide. And then as it moves up and down, all these wires will face cyclic bending stresses. Further, you will see a fretting due to the contact of the bottom of the conductor with the face of the suspension clamp, this bottom face of the suspension clamp, and also with the upper face of the suspension clamp. So you have fretting contacts in this, looking now at the right, top right of my slide, you will see that you can have contact between the aluminum wire and the clamp upper part, but also you can have contact between the wires themselves, right? In the vertical direction and in the horizontal direction, okay? Also, you can have, if this conductor is a aluminum conductor steel reinforced, you may have contact of the aluminum wire with the steel wire, and all these black points here are points that can develop fretting fatigue cracks, okay? So that's the way the fretting fatigue problem takes place in the connection between conductors and clamps. Here I'm showing to you a real problem that we got here in the Central West region of Brazil, where you can see we had a twin vertical conductors configuration. In this line, you can see that the terrain is very flat. So it's very, this type of terrain is very dangerous for fretting fatigue problems because you develop laminar winds. And then with these laminar winds, you have this formation of these vortices that will provoke this high frequency, small amplitude movements of the conductor. And here you can see in the bottom, in the bottom of the slide, that you have many cracks and failed wires within this connection of, this is a spacer, a ridged spacer, and inside the connection between the conductor and the ridged spacer, we have many fretting fatigue cracks and failures, okay? This caused a big damage to the transmission line because the penalties due to the stop in the transmission, sudden stop in the transmission of energy. This is the regulator in Brazil imposed very heavy penalties for that. So it had a very bad financial result. This is the typical form of the cracks in these problems. So you see that they always start within fretting marks, and these fretting marks look like that. Now, what is the traditional and basic way that people try to estimate the life for these conductors within transmission utilities? So usually, here I show in the bottom left, you have the towers. Then we install a sensor. This blue point is a sensor that they call vibration recorder. Is this equipment in the top left? So when the wind comes, hits the conductor and forms the vortex shedding, the conductor will be vibrating. In this vibration recorder will collect the signal of the displacement in this specific point of measurement. This point of measurement is defined by standard, an IEEE standard, okay? But you know, we don't like to work with the displacement, so we convert these displacements in time variation of stresses using this specific formula that we call Pfaffenberger and Swart formula. And then we can, after converting it to stresses, we can apply a rainflow type of counting process, and then we can go to transform. So we use this rainflow just to transform this very random type of signal in something more controlled with a fixed amplitude and period. Okay, after that, after we apply rainflow, we then go to the laboratory. We develop some SCN curves for this conductor and clamp, which should be the same as you have in the field, and then you can apply a accumulation damage rules such as minor to record to compute the amount of damage caused in the field. Okay, so we accumulate the damage, and then by using this sort of very traditional fatigue approach, SCN approach, we can then estimate the residual life. We should have in mind that these stresses computed by the Pfaffenberg-Swart formula that is applied to this time distribution of displacement. These stresses are nominal stresses, okay? And they claim to give the value of the stress at the wire, which is opposite to the last point of contact between the clamp and the conductor. Of course, in reality, it's not these stresses that are breaking the wires, because you have very complicated stresses generated by the contact. It's a much more complicated problem, but this is a nominal stress approach to try to compute a residual life. Okay? Right, so now we will try to introduce something more scientific and more detailed way of estimating life for these components. Okay, the idea is to try to do it using the wires of the conductor themselves. Okay, very limited work has been done to incorporate this new technology that we use in fatigue and in fretting fatigue to estimate the life for these components. So that's why we want to go for it. Let me run here As you saw in the nominal approach, we need to run some tests, and even to validate our methodology, we need some tests on real conductors. So I will show to you a brief move how we do these tests directly with the conductors. We have 3 banks. The shakers simulate the aeolian vibration, the load provoked by the aeolian vibration, and at the end we have these dead weights to keep the mean stress in the conductor constant. Okay. Another important thing to see is that the test is displacement controlled, and the failures always occur inside the clamp. So we use distortional sensors to detect the failure of the wires when they occur. Okay, let's move on. Right. So here we are going to present a more refined strategy to try to approach this problem. So we are going to use here a critical plane criterion, the Smith-Watson-Topper parameter. We could try another. In this case, we have seen that the Smith-Watson-Topper parameter works quite well for to estimate life of these aluminum wires. Okay, so we consider the Smith-Watson-Topper multi-axial fatigue parameter, which is based on the idea that crack initiation is controlled mainly by the range of normal stress to a specific plane. So we need to search for many planes and find the plane which will maximize this product here between the amplitude of stress and the maximum normal stress to this plane. Okay, so this is the Smith-Watson-Topper criterion, but we have considered and present this in many talks that fatigue is not a problem, mainly when you have fatigue in the presence of stress gradients. You should not consider the fatigue problem as a punctual, as a material, a single point material problem, but the fatigue problem should be considered within a process zone. The size of this process zone depends on the estimated life for this component. So you should compute these damage parameters as the Smith-Watson-Topper, not in a single material point, but within this process zone. Okay, so this process zone is an average, gives you an average of the severity of the damage for this specific material. So what we do to consider that is to use the theory of critical distance. In this case, we are going to use the volume method, and we after, when we have the contact of the wires, we will find the most severe loaded point on the elliptical surface that will be formed, and then in that point we will build this process zone, right, and integrate the stresses within this volume to obtain an average stress tensor, okay, within this blue region. So that's the strategy that we are going to use to try to estimate the life for the contact of these two wires. One important point is how to determine the L against N relation. So it's the size of the critical distance, how the size of the critical distance relates to the estimated life. For that, we need to develop two set of tests, okay? So the first one, we are going to take notched wires. So we will take wires from the conductor, apply some sort of notching them, and develop a SN curve, okay? So let's see how we get the LN relation from this test. Let's choose this red point, okay? This red point has a amplitude, nominal amplitude of stress that is developed during the test, and this will correspond to our observed life, the life for failure of the wire, okay? So it's a test in a wire like this one with a V notch here. We apply this nominal stress at the top. We have a finite element model running together with this problem. Then we guess the size of this process zone at the beginning. We integrate, get the stress tensor, the average stress tensor within this process volume. And then from this average stress tensor, we compute the Smith-Watson-Topper parameter. In parallel, we will be running tests with wires that are plain wires, okay, without any type of notch. And then with this second set of tests, we can develop a Smith-Watson-Topper against life relation. And then now I can get the Smith-Watson-Topper computed in this process zone, enter with it in this SWT against N curve, and then I obtain I estimated life. Okay.
Alex,
yes.
Apologies for interrupting. We're about 19 minutes, so just to let you know, if you could start to sort of move on a little bit faster, please. Sorry.
Okay. Thank you for warning me. And then if the life is the same, we have the correct L, and then we have a point in this L against N life, okay? So, and we keep doing this for many points. Now we have the procedure to estimate the life in the wires themselves. So first we estimate the LN curve, then now the procedure to estimate the life. This, as I have already mentioned there, I get the most stressed point. In this point, I guess the size of a process zone. I integrate the stresses there in this process zone, and then I enter with this, I compute the Smith-Watson-Topper parameter, get the estimated life. Simultaneously, as we need to guess the L at the beginning, this L corresponds also to a life in the LN curve. If the life estimated in the SWT here is equal to the life of the LN relationship, then we have it means that we guess the correct L size. If not, we keep doing, okay? When we get the correct estimated by SWT life equal to the LN, we have my estimated life for these components. Well, then we went to the labs, we ran tests to obtain the LN curve considering a hole and a V notch like these ones. The results of the test with the notch show here. You can see in the coordinate the L size in the X direction life, and you can see that both curves are quite the same. So the L against N life does not depend of the shape of the stress concentrator. This we did with this machine where we had the two wires pressed together by the actuator 8, actuator 7 pulls up and down the specimen, right? And actuator number 1 in the machine here on the left is a 2 hydraulic actuator threading fatigue machine. And actuator 1 will apply the threading fatigue load, right? So the tests of the wires were conducted in this type of machine. And here we can see the broken wire with this type of loads. The normal load was 250 and 500, two set of tests, 29 degrees of inclination between the wires. And you can see that the failures occurs within the fretting damage area, okay? Then we did this finite element simulation of the wire itself. You can see that using the Smith-Watson-Topper parameter, the most stressed point coincides quite well with the position of failure in the lab. And then we apply this methodology to obtain estimated lives. And in these two graphs, what you see is the estimated life for normal contact load of 250 and 500, okay, blue for 250, red square for 500, and in the left graph, I have the estimated life against the observed life when I use the LN curve obtained with the V knots. On the right is the same, but I use the LN curve considering the transverse roll knots, and you can see that the estimates are quite nice within a factor band of 3, okay? And to conclude, is basically that the lives were estimated were quite satisfactory within factor boundaries of 3. And they are not, these estimated lives are not altered by the data used to calibrate the fatigue model, either if it's a V notch or a whole notch. The lives were very similar. And well, at last, to conclude, the idea is that we can get the normal loads, the shear loads, and the bulk fatigue loads that will occur in one single wire, doing a finite element analysis of the full cable clump, and then extract them and use this methodology to predict the lives for the wires. Okay, so thank you. Sorry to be a bit longer than I would like. Thank you, Sam.
No, thank you. We'll just, it looks like we don't have any questions from the chat, so I'll just sort of ask a quick one. So in terms of this, you found greater accuracy by then going to your finite element analysis. What other factors do you think you need to take into account of in order to better improve future accuracy of other models for this? You know, in terms of numerical modeling or your finite element.
Yeah, the problem here is really to get a nice finite element model for the real conductor clamp, because there you have hundreds of contact zones, right? So the process is extremely expensive to model. But what we need to do, in my opinion, is to know quite well from the laboratory where the problem occurs. So we have a number of maps of the fretting failures for different types of cables and conditions, so that you can try to model specific zones of the contact to reduce the computational cost. Also, we need to use more sophisticated sub-modeling analysis to make it faster and doable.
Okay, that's great. Thank you. I think with that, we're going to have to move on to our next speaker in the interest of time. But thank you very much for your talk. Yeah, very interesting indeed.
Thank you.
Stop sharing your screen. Okay, we'll just remove you from the stage for now, and we'll welcome our next speaker. So our next speaker is Dr. Emily Schneider from Optimal Instruments. She has worked at Optimal Instruments since 2017, based in Munich, Germany, as head of sales division 1, and is a lubricant expert. Excuse me. She has more than 25 years of experience in research development at various companies, such as the Austrian Center of Competence for Tribology, Lukoil in Austria, and Lenzig AG, also in Austria. Her education, she was at the in technical chemistry at the Technical University of Vienna, and holds a doctorate in organic chemistry. She has more than 25 different publications in the field of tribology and others, and 1 patent in the field of ionic liquids, and 1 nomination as Researcher of the Year. Okay, let us welcome Auni to the stage. You bear with us for one moment. I think we would just need to set up another screen share session. There we go. Welcome.
Thank you very much. I would like also to share my own presentation.
Please do so. I'll stay on stage for a moment till I can see that. I'll just go ahead and set that up.
Okay.
Okay, excellent. There we go.
Can you see?
Yes, I think if you just put PowerPoint into, just begin the presentation.
Yes. Okay.
Fantastic, thank you. One thing to note, please.
Yeah.
There's that little pop-up there. Could you, I think there's a button that says hide or dismiss on the event.demio there. Oh, no, not that one, sorry. Could you bring there's a little pop-up that's just obscuring part of the slides. If you could share your screen again, please.
You cannot see my screen anymore?
No, no, the screen share turned off.
Sorry for that.
Okay.
Sorry, I was thinking you can see it.
No, it's okay. I could for a moment, but then it turned off. Whilst we're doing this, just to note for everyone in the audience, all of the poll questions are now available. If you haven't answered any of those, please could you have a look in the polls tab, and during Dr. Snyder's talk, I'll begin releasing the handouts.
Gesamtbildschirm teilen. Can you, yeah?
Not yet. I think it's probably just coming up.
I can.
There we go. Yep, I can see that. So okay, great. If you could just go to PowerPoint, please, and put that into presentation mode, and we'll begin.
Okay.
Okay, that's just and then just begin the presentation. And
what do you want me to do? Sorry.
So it's not in presentation mode yet. We can just see the standard. Yeah, sorry. Okay, that's
okay. Let's start.
Great. Okay. Thank you very much.
Good afternoon from my side, and thank you again, Sam, for this great organization and your kind introduction. Many thanks for the previous two great presentation, which was very scientific, very exciting. And now it's my pleasure to go a little bit to more practical part for you. We are about the fretting test according to a standard method ASTM D7594. It would be a review for you. First of all, I'm going to talk about the test parameter of this very nice standard method, the highlights of the 3 or more projects which we have done with industry at our company. I'm going to go through the highlights, for example, about the various greases at different temperature, measuring the electrical contact resistance, and of course, some example for the fretting test with a survey beyond this standard. Here, this picture shows you what standard we are talking about. That is ASTM, and if it is available for you, and you can achieve it if you want. The test parameters of this wonderful standard method is summarized for you here. At the right side here, you see the test champ of our SRV, which we need for doing this standard method oscillation movement. And in this standard, you are free to choose the temperature between 50, 80, and 120 degrees Celsius. Of course, the stroke is very low, 0.3 millimeter or 300 micrometer, the frequency 50, and the load is 100 Newton, which you have a Pmax for 2.16 megapascal. And I would like to mention that this standard and also another one from SRV is now specified since December 2022 for the labeling of the greases. For having the high fretting protection, they have to pass this fretting test at least at 50 degrees Celsius. Just like also to share with you a few words about the research report done on the round-robin test in 2021 and 2022. With this standard, there were 40 participants. Of course, all of them are SRV users, and they make this round-robin test for 6 different greases. summarizing for you the result of this report, which shows that the repeatability and reproducibility is very good given in case of fretting coefficient of friction, fretting friction, and of course fretting wear on the ball in this case. Here, this slide is a very, very simple example for this fretting that you can see how it works. Adjusting this parameter, running the test, you can see here immediately on your monitor from the SRV machine that the coefficient of friction value is very nicely stable during all 4 hours. The time is 4 hours and 13 seconds for the running in. And having a look under microscope to check the wear score on the ball and on the disc, you see in the case that you have a very high fretting protection system, or let's say greases, you have a very nice protection here. For a low fretting protection system, or let's say your coating or your alloy or your grease is not a good fretting, has not a good fretting protection. After a short time, you have an adhesive seizure here. You can see it very nicely also under microscope, lot of pitting here, and it reflects also directly in the fluctuation of your frequency during the test. Actually, very, very obvious, nice working very nicely, this standard method. Now we go through a little bit, introduce you about our internal project, which I can go to more details about them. We had many different greases. We tested them at different temperature, 50, 80, 120 degrees Celsius, and we have done all the tests 2 times. Repeatability was given for all of them, as I mentioned before, and we add electrical contact resistance sensor for some of this project, not for all, for some of them, but should be mentioned here that this measurement is not mandatory in this standard. Why we add it? Just for your information, because this value, this electrical contact resistance value in lubricating greases especially, depends on the chemical composition of that. And mainly, of course, additive and also even thickener. And that is should be mentioned here that this value can be also tailored. For those of you who are as a chemist or for lubricating, you know that it can be also tailored, for example, by adding electrical conductive particle like graphite or using a special base oil. Short, very, very short, one slide about this sensor. It's very, very simplified here, the principle. We apply a current, very, very small current between 1 microampere to 200 milliampere. In the upper specimen is a ball, lower specimen and the disc, and it goes through this intermediate, which can be oil or greases. And the voltage across the disc and the ball is measured, which is also approximately 10 microvolts to 3 volt, and the corresponding resistance would be calculated from the software, and you have this value in 3 forms: minimum, maximum, and mean value. We are going to see on the next example always the mean value. Start with project 1. The project 1, we had 2 greases with different composition and energy I group. One was based on polyglycol and lithium complex and had an EPAB sulfur compound. Energy group 2 and had from initial electrical conductivity was higher than the grease 2, which is a mineral based with lithium complex again and has a zinc component as additive, EP additive, and energy I group 3. Okay. As I mentioned before, we add also in this project the electrical contact resistance sensor. You can see here at the left side at the result of this testing, fretting test at 50 degrees Celsius. Okay, let's say Grease 1 and Grease 2 a little bit different on coefficient of friction. Okay, it's normal. But the huge difference you can see here in the values of the electrical contact resistance at 50 degrees Celsius. This increases and stay a little high. And looking on the wear score on these two greases, grease 1 with higher electrical contact resistance has much better fretting protection than 2. At 80 degrees, very interesting. It's also mentioned for those who are in the field of tribochemistry that the tribofilm composition change always between in the different temperatures. Coefficient of friction rather the same, but here we don't have also for grease number 1 a high electrical contact resistance in both cases, not a good fretting protection. However, when we go to 120 degrees Celsius, we have much more stronger and higher electrical contact resistance value in grease 1, which has a very, very, very nice fretting protection in compared to grease number 2, which stay always in all the cases in the old temperature at very low values. Saying that, we had made a little, very, very short investigation on tribofilm because we think that it's related really to tribofilm building by using X-ray photoelectron spectroscopy with our partner in IC2T in Austria. The grease number 1 shows a little bit better distribution, more homogeneous distribution on the sulfur and also a little bit patchy on phosphor. In the case of grease 2, both these elements distribution as fluctuating. And when I summarize for you the result or the insight or the information might be interesting for you from this project is that this is an electrical contact resistance sensor is really give you a valuable additive information. It varies due to the temperature. And if you can, because we have a long time of test, which is 4 hours, we believe that it is also related to the different tribofilm building. As you can see here, summarized here, grease number 1, 50 degree with a moderate electrical contact resistance, good. Very bad, very low electrical contact resistance, and the best one is 120 degree with higher electrical contact resistance. And for the grease number 2, we had no friction, no fretting protection at all the 3 temperatures. Okay, now we change to project number 2, which related to the behavior of solid particles as grease component at various tribological contact and temperature. But I'm just going to concentrate on the fretting investigation, not the other tribological investigation, and I'm going to concentrate on this special nanoparticle inorganic fluorines like tungsten disulfide, which I'm going to name it as nanoparticle in the next. Of course, it is a very huge topic in the industry, especially in the lubricant industry, using these particles as solid particle in formulation. And just for your information, because as a chemist and you have to always inform about the different products you investigate on. We have 3 groups of greases. Grease group 1, all of them was naphthenic based and lithium complex as thickener. The grease B series were naphthenic plus polyalpha olefin and a lower viscosity, and again lithium complex. And the grease group C was naphthenic base oil and moderate, let's say, or low viscosity, but they have polyurea as thickener. I don't show you all the result of all these 10. We are concentrate also one example for C and examples from the B. Grease B, the first one, without any additive, Of course, no protection, ferritin protection can be seen here nicely at 50 degree and 120 degree. We have absolutely any ferritin protection. By adding additive CDDP, which is also very commonly used additive, also with a good anti-wear and EP production, you can see that we have a very nice constant coefficient of friction value, and of course electrical contact resistance. This orange curve is also increased, and very nice protection can be seen on the wear score on the ball and on the disc. For this grease, if we go to 120 degrees Celsius, very interesting phenomena can be mentioned here, which also I have seen it is mentioned also in the literature, that we have higher coefficient of friction value at higher temperature, but it is nice and constant, and the huge increase in the electrical contact resistance. However, we have here also a little bit higher values on the wear score on the ball and on the disc. Very interesting formulation is the grease B, naphthenic polyalpha olefin, and this nanoparticle, this special nanoparticle. It works fantastic as at 50 degrees Celsius due to different tribochemistry. I don't go through that in details, but you can see here very, very constant friction value and very low, actually, low or constant electrical contact resistance. We destroy all this protection at 120 degrees. There is no protecting film at this temperature. Adding to this formulation, CDDP, interesting phenomena can be seen at the beginning. First, zinc didiophosphate is here. The competition started here with the nanoparticle, and it is somehow electrical contact resistance is coming, and the value gets stable and moderate, let's say moderate wear values. At high temperature, the phenomena of zinc didiophosphate coming overheld that here, and you can see the same phenomena as before, as we had only zinc didiophosphate at the formulation by higher temperature. This grease is also very nice. I want to just show you one example for this series. Grease C, CDTPP, and this nanoparticle has also good results at 50 degrees. Very nice result at 50 degrees Celsius, and also nice friction value at higher temperature, 120, but again, a little bit higher wear values because of temperature and CDDP. Okay, how we make a ranking? We want to evaluate and find a model to evaluate all these results, and it is we said, okay, if it is a low to medium, we give the ferritin protection is a 1+, for a good protection 2+, and for very good protection 3+. And then you can see here there are some grease formulation that get the 3+, B3 or C1, even at higher temperature. Just again, we believe that all these results, related evaluation of electrical contact resistance, related really to the building of the tribofilm, the composition of tribofilm, the time of its formation, and also its stability, which can be proven, of course, by tribochemical investigation. The project 3 is an older project, which we have, some customer gave us these 6 different greases, mostly based on PRO. The last one is the polyethylene, perfluorita polyethylene, which is also not without any additive. The other 4, they have different additives. EP, CDM1, they only have anti-wear additive. But the severe condition, which we mentioned here, related to not only very low stroke, but also much higher temperature than we were used to have for this test, 150 degrees Celsius and 400 Newton load. I summarize for you all the results of these 6 Greases, I made two groups. Let's say we compare now the soap greases and non-soap greases, and this exotic one without any additive, which obviously has the highest friction and highest wear value. The both ones we have done again two tests, and in this case, I would say the best one is grease number 5, polyalpha olefin and a special anti-wear additive, and also reflected in the very, very low, very nice wear volumes after this test. Altogether, summarize again for the project 2 and 3. We have seen that this nanoparticle has actually a good ferritin protection, but at lower temperature, bringing CDTO to the system according to our knowledge or our findings. Let's say that the electrical contact resistance increased and they overlap the effect of this nanoparticle. And of course, the results show of this standard method is very useful for the formulating very good anti-ferritin greases. And measuring again of this electrical contact resistance give you an added value for more targeted formulation. And you have seen in the project number 3 that you can use even this ferritin test for more severe condition, like much higher load and temperature than it is written in the standard method. One example beyond this standard method is the ferritin wear of the coating and the material, which also can be used by using SRV. One very nice example I brought for you is from the work of Dr. Kafke from BAM. And he measured the topic of him is hard coating with and without DLC top layer in ferritin test. The tribological characteristic of the ferritin wear and ferritin friction at different climate, he has done in different humidity and using ball and disc. The ball was not 100 chrome 6 aluminum oxide, and it was not lubricant, without any lubricants, dry system. But he has different, again, summarize for you, his parameters are a little different from the standard, 0.2 millimeter at room temperature, 20 hertz, and very, very low, much lower load than we are used by having lubricated system, only 10 Newton here. And he has 3 different relative humidity, 3%, 50%, about 50%, and 100%. And summarize for you one example of his work here in case of the coefficient of friction and wear score of titanium nitride plus diamond-like carbon disc under 3 different humidity. Very nicely, you can see the effect of the humidity here. Low humidity, very high wear volume, and higher coefficient of friction. And with 100% humidity, you have a very nice ferritin protection with this material and very low wear values. Okay, now I am on the end of my presentation, and you see only 2 slides more, which are not going to go through them, just to show you that there are a lot of papers. I found only 200, but I'm sure there are more, papers regarding ferritin test and SRV. Some of them are summarized for you here that you can see you can done this with many, many different alloy, Inosel 600 alloy, nitride steel, and many more with non-lubricated or non-lubricated system, and they are from the very good research institute and published in the very good tribology magazines. The second slide also come for you again that you can see here. You can also do this for the special polymer in this paper here, and also again Inosel X750 and much more. In case you want to have all of these papers to read, please contact me if you want to know more about our own project, which has summarized for you the highlights. please contact me. And here is my contact address, and I want to thank you for your kind attention and happy to answer one or other questions.
Thank you very much for that talk, Amine. Sorry, I just popped on stage to I think as you were starting to wrap up, say we're at about 20 minutes. So we have one question which we'll do quickly now before moving on to our next speaker, just in the interests of time. So I'll just stop sharing the screen for now. So I think
okay, thanks.
This
now I see you and hear
yes,
you.
Yes, here we are. So we've got a question here from Shashank, who asks, how would you relate ECR with the Strieback curve in boundary or mixed? I wonder if there is any relation we can make there, but sorry.
Yeah, okay. We have done all this not it's a mixed regime, not in boundary regime. If you want to do that in boundary regime, you have to go to the ball on disc system, which we offer also with SRB. But all my project was oscillation movement. Yeah, within the oscillation movement, you are always in the mixed regime and not in boundary regime. Okay.
Okay, that's great. Thank you. So thank you very much for your talk. And just to note for anyone in the audience, for those papers that you highlighted, anyone who's registered for this event, you will receive a replay of this. So you can go back through, you can pause at those slides, take a look at those papers. Of course, Dr. Schneider's email address is also available in that replay if you want to get in touch any further.
And as mentioned, if they want to know more details about my project, they are welcome to contact me anytime.
That's great. Thank you very much. So let's move on to our next speaker now, Professor Michael Bryant, University of Birmingham.
From my side.
Goodbye, Amine. Thank you very much. Professor Bryant is Chair of Tribology and Corrosion Engineering at the School of Engineering, University of Birmingham. His research focuses on multi-scale aspects of tribology materials characterization, both engineering and natural materials, and mechanical interactions of materials interfaces used particularly for, but not limited to, biomedical applications. Michael's currently developing research and teaching activities devoted to modern aspects of corrosion tribology, surface science, and applied biomechanics. This includes surface chemical effects and energy production, biotribology, biocorrosion, and methods of mitigation. His research is concerned with understanding and optimizing the interactions occurring at interfaces commonly found in many applications. In particular, he's focused on the development of advanced testing methodologies, incorporating in situ techniques to assess interfacial processes in real time. Welcome to the stage, Mike.
Cheers, Sam. Thank you very much.
Sorry, just trying to get through that in reasonable time.
I know. If I knew that you were going to read it out word for word, I'd have sent you something a bit less wordy.
It's okay. I'll try to read quickly, but no, it's okay. I just want to make sure that everyone gets a good introduction. So there's your slides up now. Stage is yours. Take it away.
Great. Well, thank you very much, and it's great to be able to contribute to this event and follow some esteemed speakers as well in the area of fretting. So as Sam mentioned, my name's Mike. I used to be at the University of Leeds until very recently, and I've now moved to the University of Birmingham, where we're pursuing similar endeavours, but also then looking to expand some of our research interests into other domain areas. This afternoon, I'll principally be talking about the fretting corrosion of biomedical devices, which is something that we've worked in for a number of years. And when I say we, I mean the team that underpins it. I can see that there's a few guys from Leeds here, existing PhD students who are due to be finished, and ultimately they're the guys at the coalface doing that work, and I get to just repeat the work that they're doing and bring it to the fore. So it'll be principally talking about the work that we've been doing in medical devices, and particularly around musculoskeletal health. And the drivers for the research within that group are mainly based on the worldwide musculoskeletal health burden, which affects around 1.7 billion people worldwide. And these are an emerging set of demands, but also an emerging set of challenges for devices. But the costs associated with with this burden is huge. So we're talking about 23 million lost days of work in the UK in 2020, and an estimated $30 billion in healthcare costs in the US. So the costs associated with these with these particular conditions is huge. And ultimately, as engineers, we've kind of tackled that through the development of total joint replacements and medical device interventions. You know, and particularly in the area of joint replacement, these have kind of come to the fore in the last since the 50s and 60s due to the kind of seminal work by tribologists and surface scientists in the area. So principally Professor Dowson initially in the domain of polyethylenes. But as this work as the work kind of emerges and devices have become more popular, the rollout has become a lot more popular, and ultimately knees and hip replacements are now a common day thing, and most people will know somebody that's had their hip replaced, and it's become a gold standard surgery for addressing musculoskeletal health issues. So biomedical devices are ubiquitous in modern life and play a vital role in the restoration of biological function, in restoring biological functionality. And as I mentioned, the hip is one of the most successful interventions, and it's owing to the early innovation and engineering development that went on to underpin that kind of technology development. But what we need to consider as well is that these devices, albeit relatively simple looking in their nature, were initially designed to restore functionality in principally elderly and sedentary patients, so in 80-plus-year-olds that don't really do a lot of motion. But as their success has been proved, they've now been used in younger and more active patients, which ultimately dictate a very different, which often necessitate very different functionality. The durability requirements are very different, and as such, their ultimate performance is impacted. And what we can see over the years is that we all know that every person is different, every patient is different with different anatomy and different needs. And as a result, engineers have tried to accomplish this by making devices more personalized, by introducing modularity, so connections between devices, to facilitate variations in implant design, combinations to fit anatomy and the requirements. And most kind of typical, or the most kind of typical interface that we find here, or the most common way of doing this, is introducing what is described as taper interfaces. So these are based on Morse type interfaces, and I say Morse type because they've been adopted from Morse tapers from machine element situation, but they've been varied in a way that as engineers, I think we kind of think that we know what we're doing, but in reality, we've taken a machine element and applied it in a situation where it wasn't really designed or hasn't been validated for that use. Whilst these are ubiquitous in their nature, and most devices that you'll find on the market now, and inside somebody has a Morse taper associated, or Morse type taper, there are loads and loads of different devices and different loads of different designs, surface roughnesses that contribute to these interfaces. And ultimately, by doing this, what we've done is we've increased in this modularity. We've increased the number of interfaces that are present, but we've also increased the number of interfaces where fretting corrosion can be particularly can become a particular issue. And we'll have a few examples of this as we go forward. So for those of you that aren't aware, this is a bit of an A-level introduction to biomaterials, but there are a number of materials that are commonly used for the manufacture of biomedical devices. So we've heard from Professor Shipway about steels, we've heard a bit about aluminium alloys, and particularly in biomedical applications where we're focused on cobalt-based alloys, titanium-based alloys, and iron-based alloys. And they, regardless of the application, they're the typical alloys that you would find for use in hip joints, knee joints, stents, catheterization, and so on. And they're the kind of a well-established materials that are of particular interest. There are also materials like polymers, ultramolecular polyethylenes, peaks, and ceramics as well, advanced ceramics, which are also of interest. And for things like femoral heads, ceramics are kind of coming to the fore as one of the technical ceramics are coming to the fore as being one of the more durable materials. But we'll be mainly talking about metallic materials and the degradation of these materials in this presentation. Now, the one thing that unites these materials ultimately is first of all their passivity, which is really the property that dictates their biocompatibility. So this is a very thin oxide film that spontaneously forms. So slightly different to the films that oxides that we heard about by the first presentation, but these are spontaneously formed passive films on a surface, which ultimately form a semiconducting layer that limits the rate of reaction on a surface. And the other uniting aspect is their biological environment that they work in. So first of all, just touching on the biological environment. So, you know, we've heard a lot about kind of some of the extreme environments and some of the other engineering environments, but the body itself is also quite an extreme environment. We've got you know, we take what we would describe as a passive metal, we place it in a biological environment, which by its nature is very sensitive, and it's subjected to around about 37 to 40 degrees in temperature, depending on where it's located. It's an aqueous environment in the presence of salts, dissolved gases, proteins, and various other things. And the other complicating factor here as well is that both the pH changes with time and location of that device. So when we're talking about these materials, the environment in which they're interacting with becomes particularly important. And these variations in pH and environment can have you know, have been shown to have a negative effect and a positive effect of the corrosion of these common biomaterials. So when we talk about these materials, so I'll be mainly talking about cobalt chrome alloys, and the reason for that is because they're an easier alloy for me to describe what's going on at that interface without having to worry too much about trying to explain the complex metallurgy of things like titanium alloys and well, mainly titanium alloys, which I'll leave to Pedro, who's on the call. He'll be due to publish some work very soon, looking at the kind of the complexities in the evolution of titanium microstructures under fretting conditions. But you know, with that in mind, cobalt chrome surfaces also offer fairly complex fairly complex interfaces and substructures that we need to bear in mind in terms of their degradation and their materials transformation mechanisms. So when we take a bit of a closer look, this is just a simple piece of ground low carbon cobalt chrome. You know, very basic alloy, fairly coaxed grain structure, typically an FCC based. But right at the interface, we have these nanocrystalline layers, which, you know, when subjected to shear and fretting, are subject to dynamic rearrangement and recrystallization of those interfaces, which some of our more recent work is now showing that these are intrinsic to ultimately the debris that's generated from these devices. But what we also see is that we can get this segregation within the alloys as well. So where we can have segregation in moly and chrome, which is particularly important from a protein interaction, from a selective dissolution point of view. And what we do know is that that proteins and phosphates interact with these different species, with these elements differently. And some of the work that we published recently has demonstrated that we can get preferential dissolution of these alloys just under simple static conditions. But as I mentioned, this is ultimately the crux of what we're talking about, the performance of these materials. So this is a TEM image of a passive film that's formed on a piece of low carbon cobalt chrome, and this is ultimately the barrier that protects the very reactive cobalt chrome surface from the external environment. And when this is subject to stress and fretting and various other mechanical perturbations, this layer can become cracked. Stress in itself can drive the corrosion, the reactions across that interface, and ultimately we have rapid oxidation of that subsurface. So as well as corrosion, mechanical damage at these interfaces, will cause damage to this film, and ultimately this gives rise to this mechanism of tribal corrosion, but also fretting corrosion, which we'll talk in a bit more detail. So before we kind of move on to that, I just wanted to touch on about how sensitive these materials are. So so we're talking about materials in general here that we're taking and then rubbing in quite complex environments. But even just under static conditions, we can see that things like phosphates, they're able to reduce corrosion currents because they absorb to the surface. But then when we introduce other species like proteins, particularly BSA albumin, we can see that we can also change the reaction kinetics where we get competitive absorption and ultimately drive the corrosion rates. And we also see that the breakdown of these oxide layers can be negatively affected by phosphates. But then with the addition of proteins, the protectiveness of these oxide films can be enhanced. So what we have here is, just in its simplest form, in a static condition, a very, very complicated reactions occurring at interfaces, which change how these materials, degrade and their fundamental passivity, which then when we subject them then to mechanical abrasion, then provide, adds an additional complexity in terms of then how these materials are performing, degraded, where the material is being lost, and ultimately how it's being lost from that surface. So, my perspective with many of these devices is that it's inevitable that you're going to get breakdown or detachment of these oxide films on the surface, and the extent will very much depend on the nature of the environment that it's in, but also the tribological conditions. But what's particularly fascinating about these materials, and particularly when we're talking about passivity, is that once you remove or once you've abraded that surface, the oxide film will spontaneously reform, principally because the underlying surface is incredibly reactive. The metal will react with the oxygen or any kind of any oxygen or water that's present at the interface, and then it will spontaneously reform these within these passive films. But when we have these processes occurring within tribological contacts, what we have is this spontaneous, this constant abrasion and removal of an oxide film, which we can term as tribal corrosion. And ultimately, fretting corrosion is a subset of this tribal corrosion mechanism, where we're dealing with these combined mechanical and chemical interactions within a fretting contact. And ultimately, what we have here is a situation where we can describe the material loss from that interface as a combination of both wear and corrosion. And that was initially first kind of characterized by Uhlig in the early 1900s, but later extended by Watson in the early 90s to demonstrate that we have material being lost as a result of pure wear, pure corrosion, but also then this synergistic loss between the corrosion enhanced wear and the wear enhanced corrosion. So we have these interactions which can both negatively and synergistically affect the material loss, as well as then these fundamental pure wear and pure corrosion. So from a prediction point of view, it becomes a very difficult phenomenon to predict, and from a modelling point of view, even more so. And there are a number of models that exist in the literature, but it's very rare that you find models where the physics and the chemistry are decoupled and coupled in an appropriate way, so that you can represent what's happening in that interface in a meaningful way. So particularly in the case of medical devices, components are usually accompanied by the establishment of a crevice, just mainly because of how components are put together and how things are clamped. And what we typically see is that once we have fretting being initiated, we see this elevation in the current, as we saw from the previous slide. But when we cease fretting, that current is usually sustained. And ultimately, this concept has been was coined in the late 90s by Gilbert as mechanically assisted corrosion, and it's kind of stuck in this area, which gives it a framework that we can apply to these devices, which describes this interaction between both the mechanics and the crevice corrosion that's occurring within these interfaces. But it provides quite a nice, elegant way of being able to describe and characterize what is going on in these interfaces. And what would be particularly interesting is how we can ultimately link some of the more established work that Professor Shipway presented, particularly around particle debris ejection, to then these mechanically assisted mechanisms, as this is becoming one of the more kind of pertinent challenges in the area. So as we've heard from a number of the presenters already, fretting contacts and their input conditions can greatly affect the material degradation mechanism. similar story is true for fretting contacts, fretting corrosion contacts, and we've shown for cobalt chrome self-mated contacts that corrosion tends to dominate at relatively high contact pressures and at low displacements due to limited slip and exposure of that native surface, that native reacted underlying surface. But as the contact pressure and the slip decreases, we can see that wear, or the physical wear, becomes more dominating. But ultimately, what we have found is that we can never escape this purely. We can never escape into a purely wear domain. We always have these elements of wear corrosion or corrosion wear taking place, and it's usually the case within the biomedical domain that we're usually within this corrosion wear domain or within the corrosion domain, which presents some interesting challenges in terms of how the material is released from that interface, whether it's debris or whether it's ionic. Similarly, a lot of other researchers have have used turbometer studies. Haven't covered the actual turbometers that are used in these studies, because actually they're wide ranging, and you could enter a debate as to the appropriate setups in these alone. But people have looked at other researchers have also looked at the role of materials couples. So it's very common that you get different material combinations being used in biomedical applications. So cobalt chrome is typically used as a femoral head because it's incredibly hard wearing, whereas titanium is used for more structural devices like the femoral stem. But ultimately, what has been noticed is that they play a significant role in terms of the actual fretting corrosion mechanisms. Where Gilbert and Swaminathan have actually proposed that things like cobalt alloys within titanium with a titanium contact can dominate the tribological performance, but with then things like titanium interactions are very much more kind of susceptible to the chemical component of deterioration. But the additional complicating factor in here as well is that the resulting fretting corrosion, the resulting coefficient friction, and as well as in later studies the energy dissipated and wear, is also a function of the applied potential that we test these as. And again, there's a lot of debate around how you choose a voltage or an applied potential to test that, but ultimately what we have is a way of being able to control the reaction kinetics to systematically look at what's occurring at interfaces, and then try and work that backwards to then try and optimize the device interface. And similarly, environment is being studied. So we know from a crevice corrosion point of view that the local regions within a crevice will become deaerated and will reduce the pH. And some work by researchers at Rush from Marcus Wimmer's group with Alphonse Fischer has really paid attention to these tribochemical effects, or what they determine the tribochemical effects within these fretting corrosion contacts. And as expected, a decrease in the pH can increase or can adjust to kind of affect the total energy loss and ultimately the total wear. But what's particularly interesting within these occluded cells that they developed was the role of liberated ions and how they interact with things like proteins in those interfaces to then form these lubricious and protective tribochemical films on the surface. And from an academic point of view, these are interesting because it demonstrates the kind of this mechanochemical interaction aspect that's occurring. But from an optimization and from a translational point of view, it raises again questions as to what the optimal environment, or how can we engineer these environments to give us optimal conditions within these interfaces. And from a tribological point of view, where we may want low coefficients of frictions and to facilitate slip within a bearing, for example, in these fretting interfaces, it's often that we don't want that. So it's then how do we engineer that, considering fretting as its own unique aspect. So part of the work that I've still got some slides, I'll whiz through these.
Okay,
so
great.
So part of the work that we've been doing at Birmingham is really to kind of progress this understanding. So we've been developing more advanced simulations to represent the components of these interfaces and how they degrade. And ultimately, what we wanted to address was this kind of debate in the literature around what the optimal engagement is within these tapers. So on the market, you can buy distal, matched, and proximal tapers, all of which are acceptable. They're accepted. They're on the market. But but each one of these designs has been implicated implicated in some kind of performance-related issue. Some of the work that we've been doing at Leeds and now Birmingham is developing advanced simulation methods where we can both apply standard-based testing, but also apply complex biomechanics to these, so we can apply and simulate the actual articulation around these components. But we can also then integrate sensors into here to then look at things like micromotion. So this is an eddy current-based micromotion sensing array where we can measure 3 points in the plane, look at toggling the micromotion. And also electrochemistry, and then ultimately merge the two together to give us information about what's happening at that interface, which you typically wouldn't get from standard ISO or ASTM-based testing. So when we look at the fretting corrosion response, unsurprisingly, we can see that the micromotion between the head and the stem is very different under articulation, where we have an axial force and then sliding around that head. We can see that we get more complex toggling and micromotion occurring around that head. But what we also see is that we can link the two of these together and ultimately start to understand a bit more about what's happening at these interfaces. And one of the things that we've been able to do through this framework and approach is to really answer some of the kind of the key clinical questions around how device design and clinical process, things like assembly, affect crevice corrosion. Affect the corrosion at these interfaces, and ultimately we've been able to demonstrate that both assembly matters, design matters, but also surface roughness matters when designing these. But what's particularly a benefit from us from an academic point of view is the fact that we've now got a framework where we can, first of all, where we can stratify design, but we can also accelerate R&D, meaning that the variations at a component scale in design are a bit more achievable rather than using long-term costly standards-based testing. So why are we bothered about this? So ultimately the reason why we're bothered is because the key implications are not from a structural point of view, but because they're from a biological point of view. And fretting corrosion degradation has ultimately been linked to what we call adverse reaction to metal debris and ultimately failure of the device, which requires some kind of intervention. And it's becoming more and more to the fore as metal ions released from and debris released from these devices have been seen systemic within the human body and with locations being found in the liver and the brain, and then ultimately being linked to other diseases like Alzheimer's and cardiovascular disease as well. So the implications of the material lost from these is not from a structural point of view, but more from a biological and a health point of view. And what do these things look like? Well, you know, nine times out of 10, when you take a device out of the body, they don't look pristine. You know, they tend to come out covered in black gunk, oxide layers on the surface. Demonstration of severe corrosion at these interfaces. You know, through to severe wear in some cases where you see complete material loss and wear down of these modular taper interfaces. But ultimately, you know, when you see an adverse reaction to metal debris, the surgeon is presented with a massive black gloop when they open the joint capsule, followed by a load of dead tissue, which they ultimately need to excise and then, resulting in more invasive surgery to the patient. So this is a few more examples. It's not just limited. So within the MSK domain, it's not just limited to modular tapers. At the head neck, we've also got stem neck interactions where these were slight variations in materials alloying chemistry that were changed, which ultimately led to big changes in the fretting corrosion perspective, performance of these materials. But also things like spinal screws, spinal rods, which are typically used to correct kind of adolescent deformities or in the treatment of oncological activities. Corrosion is quite dominant in those domains as well. So there are some huge potentials for device development as well as testing developments within this domain. A similar area is dental. Dental is a massive area, where you have these abutments, but ultimately you've got bone tissue, device tissue interfaces, device, and then device ceramic interactions. But the dental domain is particularly complicated by the fact that you've got more complex soft tissue structures which are sensitive to these more sensitive to metal ion release. You've also got issues around staining of tissues, which is not so much of an issue for things like hips. So it's quite common with titanium hips that you'll see staining of tissue, but it doesn't cause an issue, cause a problem. But also things like bacteria and the oral biology, biofilm formation, also contribute to ultimately the threatening performance of these devices. And more recently, one of the aspects that's kind of come to the fore is a degradation around and a deterioration around cardiovascular devices. So cardiovascular devices are a massive, it's becoming a very routine procedure for people with coronary heart disease. But one thing that has been noticed is deterioration in these devices. The fact that they've interfaced with dissimilar materials, where you have then these macromotions from the pulsatile flow, and the fact that then this deterioration has been linked with further complications around adverse remodeling around the stents. And it's not just stents that this is limited to. Things like contraceptive devices have also been implicated in similar complications. So ultimately as a medical device technology is evolving, the challenges are evolving, but we also see that the adoption of these devices and miniaturization of devices and the application to other areas also brings additional challenges. So it's a fascinating area to be involved in, as it keeps us it does keep us very busy. I'll just briefly touch on this. So we talked a lot about the kind of the mechanisms, and much of the work has really focused on the mechanisms, but ultimately what we want to do is translate those mechanisms into solutions. And one of the areas that we've been working in for a while, and with the work starting to kind of come out in the literature, is the use of hard ceramic coatings for protection within fretting contacts. And I know that there is a lot of literature out there in terms of fretting of and fretting corrosion of coatings, but specifically the application within these representative contacts is quite rare. And one of the limitations is the fact that these devices are they're modular in their nature, but they tend to be assembled by a surgeon using a hammer and a press. So any coating within these interfaces needs to withstand quite a lot of plastic deformation and a lot of brute force. And ultimately, some of the limitations around the translation of these hard coatings into these fretting corrosion into this domain is their durability within these contacts and how we can address these. And there's some interesting work that's due to be published where we've looked at kind of hybrid coatings and dual with different moduli for accommodating this plastic deformation within the interface. And again, there's a lot of inspiration that we can take from machine elements, particularly from Morse tapers, where things like compliant coatings are of particular interest within those applications. So conclusions and outlook. So fretting corrosion within the biomedical area remains a thorny problem, and its issues are kind of only just coming to the fore, particularly around testing with the introduction of more recent EU MDR medical device requirements, which now requires manufacturers to understand all debris and all nanoparticulates that are derived from an implant. And particularly from a fretting point of view, it's never really been considered as a tribological interface that can produce debris. But now what we're starting to see, including our work, is debris, in the region of 3 nanometers being liberated from these contacts. So this area is likely to kind of pick up traction and to really grow in the coming areas. But there's still a lot of work to do in terms of understanding the physiochemical interactions, but particularly those at a component scale as well. And one of the things that, as I mentioned, we've been doing is developing these frameworks where we can hopefully translate between benchtop tribometer testing through to component scale testing, and then with the modelling that goes with that. And again, there is huge scope for materials innovations in this area. Modular tapers for hips are fairly well established now, and they've been established as an effective technology. But for things like growing rods in children with scoliosis, they've been implicated in some really spectacular failure modes in the last 5 years. And you know, I'd urge you to have a look at those if you're interested. So there's some really nice, there's some real scope for materials innovation within these areas. The other thing as well is that the UK has kind of transitioned and is following the US in terms of regulatory science around these. And so now there's becoming an increased interest in how we test devices and how we understand device performance as well. So rather than it being typically a benchmarking exercise, which is what's typical within biomedical device development, there's now more emphasis around understanding how these materials perform, how these devices perform, and what the risk is associated with those devices. So with that, I'll conclude. None of this work is possible without our funders. So I'd just like to acknowledge some of the funding that we've had for this work and the ongoing work, some of which the guys are in the chat. And I'll thank you and welcome any questions.
Great, thanks, Mike. Looks like we haven't had anything just yet. So in the interest of time, I'd just like to quick question for me, and then move on to our next speaker. So I think you were talking about a number of different potential coatings to use for some of these applications. Which one do you feel has most promise? Is it DLC, titanium nitride, or do we need to look into more complex structures for these coatings?
Yeah, I think more complex structures are needed, because what we see is with DLC or silicon nitride, because the roughness of a lot of these devices is quite high. We're talking about nearly up to 1 micron in surface roughness, so they're more machine surfaces. As soon as you assemble these components, the coatings essentially come off. You see massive amounts of delamination. So I think actually when you think about it, probably hard coatings are probably not the way to go. Or maybe a combination of something that's hard and soft is what's needed. But yeah, I don't think there's a magic bullet at the moment. I think there's a bit of there's quite a lot of materials development and interfacial science development that can be done to support that kind of area.
Okay, great. Thank you very much, and thank you very much for your talk. Lots to think about. Lots of reading to do. Okay, that's brilliant. Thank you. Thank you all very much. We will now be moving on to our final speaker, Professor Sean Lean, who is established chair of mechanical engineering at the University of Galway. He was previously an associate professor and reader at the University of Nottingham from 1999 to 2008, and he did his PhD from 1999 to 2008. For associate professor, and did his PhD from 1995 to 98 with Professor Tom Hyde. Has experience in the offshore and gas industry from 1991 to 1995 at MCS International, and he has significant experience in large collaborative research projects with fundings from SFI, EPSRC, ESA, various industry collaborations, etc. Some of his specialism includes micro, meso, and microscale modeling of structural integrity, fatigue, fretting, wear, corrosion, plasticity, and manufacturing processes. So now let me invite Professor Lean to the stage. Okay.
Well, hi, Sam.
Hello.
Can you hear me? Okay.
Yes, can hear you great. Thank you very much. Oh, sorry, I think you've accidentally clicked the leave stage button. There we go.
I meant to click the start sharing.
Yes,
the screen.
yeah, not a problem.
So the entire screen I should go for, I think, isn't it?
Yes, please.
Okay, it's taking. Let me see. It's not working there at the moment now.
Just give it 1 second, or it takes a little moment to come up. Okay. Okay, while we're just setting this up for once Professor Lean's talk is concluded, while we'll be sharing the link to the attendance certificate, so you can you'll be able to generate that after this talk.
Okay, so it's not letting me share that the whole screen there. Oh, hang on a minute.
Okay.
Let me try. Oh, is that better? Can you...
Nothing yet. There we go. Brilliant. So I think if you just switch to PowerPoint and then go ahead and.
How's that?
There we go. Great. Just just put it into. Yeah, just
Okay.
swap.
Is that okay?
Perfect. Thank you very much.
All right.
Take it away.
Thanks, Sam. And if you can keep an eye on the time, Sam, because I'm
Shall
conscious
do.
people. I think we're gone a good bit over time now, but
We
I'm
have a
conscious
little,
that
but
people will.
Mhm.
Okay. So anyway, look. Good afternoon, everybody. It's afternoon in Ireland. I'm not sure what time it is where you are, but in any case, nice to meet you all. My name is Sean Lean from the University of Galway on the west coast of Ireland. Let me see if I can use my pointer here. Okay, so I'm going to talk about fretting fatigue and wear in marine risers. Okay, I won't go through the various affiliations of research groups and research centres, etc. down the bottom. In terms of an outline, then I'll just give one or two slides on background and introduction, and then I'll talk a little bit about experimental characterization of fretting, wear, and fatigue for the types of steels in pressure armor layers of flexible marine risers. And then I'll talk a little bit about modeling of fretting, wear, and fatigue interactions for the same materials, for those materials and those applications, which are marine risers. And I'll have a little bit about global to local modeling as well. And then finally, as indicated in the lessons that we would say we would teach you, I said I'd mention something about micromechanics of fretting fatigue for these kinds of steels and applications as well. So just a little bit of background then. Basically, this shows, you can see the image in the top left shows a particular typical offshore oil and gas application. And the kind of structures that we're looking at are on the top right, you can see a cutaway section of the kinds of flexible marine risers we're talking about. And these are really important structures because, of course, if they fail, like I suppose any of the structures involved in oil and gas extraction, we can get the kinds of problems that we see down the bottom right, which is the Gulf of Mexico disaster, which of course was very expensive, particularly to the environment, but also economically to BP company in particular, for example. So essentially, we're focusing on the pressure armor layer, which has the particular function of resisting the internal pressure, the hoop stresses, really, the internal pressure in the due to the hydrocarbons on the inside and the hydrostatic pressure on the outside of this structure. But at the same time, it needs to allow articulation because they're called flexible risers. They've developed essentially to allow greater motion of the vessel and more complex sea states, etc., and deeper water extraction, etc. So down in the bottom left corner, you see a kind of a simplification, a schematic of the kind of structures that we're talking about, a kind of repeated unit interlocking zeta layers, giving rise to, in particular, to a nub groove contact region, which is the focus of our work in terms of fretting. And the kind of key parameters that are important there are the external pressure, the internal pressure, and then the curvature due to the bending of these structures, and then, of course, relative displacement delta, which is cyclic in a typical situation where we've got a hydrodynamic loading due to waves, current, vessel motion, etc. Then we're also interested in delta. So that kind of leads to the kind of fretting situation where we normally think of some kind of a clamping load on a structure with some kind of tangential cyclic displacement. So some kind of a clamped assembly with some kind of tangential cyclic displacement leading to that kind of fretting situation that a number of the presenters have talked about earlier. The kind of framework that we've tried to develop here to tackle this problem for flexible risers, I'm going to just show in this slide. And it really consists of computational, but obviously motivated by experimental and informed by experimental characterization. So the experimental box is down in the bottom, and we've conducted a riser dissection, which I'll show a little bit in a minute. And we've essentially extracted test specimens for the riser material from that. We also got raw material from the materials manufacturers of the wire that's used for this. And then we've also developed a fretting wear test rig at Galway as part of that. And in fact, just to point out, in fact, the PhD student who worked on this, Sinead Halloran, actually spent time with Phil Shipway at Nottingham learning about the fretting equipment there. And then in terms of computational work, we've got global models and local models, and indeed analytical models, which are much more computationally efficient than, of course, than finite element computational type models. And then we've linked that to the kind of work that that Alex showed from Brazil on multi-axial fatigue modeling. And we've talked a little, and we've also incorporated wear effects. But of course, I'm using the Archer wear model, which Phil has already explained isn't the best model. So we really need to upgrade that. And then, of course, that's characterized by fretting wear tests and fatigue tests, etc. And ultimately, then we link the various key parameters, friction, fatigue, wear parameters, into a wear fatigue model and come up with a design tool, which is the kind of objective. I won't spend too long on this. You can find the details in our papers, etc., or Sinead's thesis. But this is our fretting rig, which is has a piezoelectric actuator, which you can see here, that drives the tangential displacement. It's a cross-cylinder arrangement where basically we've got two cross cylinders with another one which moves in and out basically. And there's a normal load applied by a dead load. And you can see, three cross cylinders in total, two of them, one above and one below a test specimen, which is then cycled tangentially between those. And then there are various, sensors, etc., there to measure displacement and to measure force, and that's implemented in a closed loop control system via LabVIEW data acquisition. And then you can see a little bit more of the detail of the actuator and the force sensor in the top right. And then the bottom left, you can see the assembled 3-cylinder arrangement with the dead weight normal loading shown there as well on an additional view. And then some of the test parameters are shown here in this table. Displacement amplitudes of about 1 to 6 microns, 300,000 cycles typically test duration, and loads giving pressures of up to 1700 megapascals, quite high pressures in these cases, and the oscillation frequency about 2 hertz. And then the riser dissection, I won't go through the details of that, but it was quite a complex process, and that allowed us to extract out material specimens. You can see the typical dimensions of the zeta layers here, about 10 millimeters for that typical dimension there. And then here's some characterization of the composition of the material. And then really I'm showing here some strain control fatigue test results in the bottom left. These are the stabilized loops for different low cycle fatigue strain control tests. And then you can see here the stress evolution in those tests ultimately leading to failure. And then you can see in the bottom right the typical Coffin-Manson type strain life, plastic strain versus life data that we obtain from that, and the kind of fits that we use to help us in our modeling. And then just to show you an example or some sample of some of the fretting results from the pressure armor layer material shown here, that we've characterized gross slip and partial slip. And these plots here show the evolution of coefficient of friction for a range of different normal loads, typical of what's expected in the pressure armor layer contact nub groove region. And then you can see typical wear scars from our cross cylinder tests now in our fretting, in our piezoelectric actuated fretting rig. You can see the typical measured profilometry wear scars. Lots of challenges around that. I won't go through the details of that now. And then in the bottom right, you see typical what are called fretting loops, which show the force displacement, basically response, energy hysteresis response, if you like, and the kind of displacement that we've controlled down to about plus or minus 2 microns in this case. So that's showing some sample results from the experimental characterization. Then I'll talk a little bit about the modeling. Now, there's a range of different models used, but one of the first models we started to work with was a fairly simple axisymmetric FE contact model. We'd had a lot of experience with contact modeling. So, the main thing here is to try and capture some of the various layers within this flexible riser, not just the pressure armor wire, and to capture some of the loading. So the applied tangential displacement, which is the delta applied in the vertical direction there, internal pressure, external pressure isn't labeled there, but it's captured in the model as well. It's included in the model. In the bottom left, you can see we've actually modeled plasticity in this, and this is a comparison between our plasticity experimental strain hysteresis loops as measured and the finite element representation of those. And you can see that there's a cyclic softening behavior in the material, so that's represented in the model as well. And in the bottom right, you can see the images of the basically of the how can I get out of this thing here? So there's a little animation there which shows the kind of cyclic behavior that represents the fretting behavior in the nub groove contact region of the model. And then in the top, you can see we've looked at the effective coefficient of friction, because coefficient of friction would change as a function of various parameters in the fretting situation, such as normal load, stroke, number of cycles, lubrication conditions, etc. We've looked at a lot of that, but I'm not going to present the details here. And then, as I said, the next step then really was to incorporate the effective wear into the nub groove contact modeling. And that's what this flow chart here shows. And again, as I mentioned, I'm showing the archard wear model is what's implemented here. We've actually implemented an energy wear model as well. And it seems to me that based on Phil's talk earlier, we definitely now need to look at a slightly more complex model, that these non-Archardian type models, if we really want to represent the physics more accurately. And ultimately, you know, what we're looking at is we're looking at a cycle counting or a cycle stepping type approach, where we accumulate various numbers of delta n cycles, and we calculate the wear during those cycles, and we also calculate the fatigue damage during those cycles. But in this case, I think this slide here is just showing the updating of the wear of the contact geometry associated with the wear. And in the bottom, you can see a sample comparison from Sinead's work. Sinead O'Halloran is the PhD student who did this work, between her finite element model and the measured profile of the wear scar, giving reasonable comparison, I would say. And then, you know, you might ask yourself, well, why should we bother caring about wear? Is it important? And I would say, yes, I think it can be exceedingly important. In this particular case, I'm showing some examples which show perhaps, well, I was going to say pretty extreme wear, but actually about 8 microns worth of wear in the top left after about 200,000 cycles. And then what you can see is in the top right, you can see how the Hertzian contact pressure reduces as a result of that, and the contact scar widens, as Phil showed examples of experimentally, and you get a much reduced pressure, a much more uniform pressure. And then, of course, what that leads to is a changing, evolving sigma xx and tau xy stress distributions across the contact region. And in this particular case, if it's a gross slip case, as it is here, then the stresses actually reduce. So that would mean if you didn't take account of this, you would be overly conservative, for example, typically. And then we've basically implemented that then with a fatigue damage model, which is the Smith-Watson-Topper model that Alex spoke about earlier, which is an established high-low cycle fatigue model. It combines high and low cycle fatigue, also includes the effects of mean stress. And in this particular case, we've included some of the aspects that Alex spoke about, in particular the critical plane aspect, where one tries to apply a more circle type stress and strain transformation to identify the worst critical or the worst plane or orientation for this parameter. But another key aspect here that we've included is we've included this fretting damage term, which we've previously developed in the work of Ding et al. When I worked at the University of Nottingham. I think Phil was involved in that work as well, actually. And that approach basically allows us to, there's two approaches here. You can do a time-consuming finite element U-mesh motion, the blue dots here, where we can see how the crack initiation life varies with stroke, with this applied tangential stroke. And we can see there's a reduction in life with increasing stroke initially due to partial slip and transition to gross slip, and then an increase in life and a leveling off of life with further increasing stroke in pushing up into a gross slip regime. And that's captured, that's a time-consuming approach to blue dots if you use a finite element model with incremental cycle counting approach that I mentioned earlier. But what we're saying is that you can replace that by this defret parameter, and that's much more efficient. And you really just need to do one analysis, one finite element analysis. You don't need to simulate a cycle counting type approach. And then we've combined that also with that typically we use that to predict crack initiation, as long as we use a scale consistent approach. But then we've also included fracture mechanics with weight functions and mixed mode fracture, as you can see here on the right hand side, to include crack crop propagation. And what that then allows us to do, I'll show later, is to distinguish between crack initiation and total life. Then we've looked at real hydrodynamic models, and I won't show any simulations of the models, I don't think here, but you can see an image an image here of the kind of ship, and this is called a spar type arrangement for the flexible riser floating production system here, FPSO type application. And we've looked at a bunch of design load cases for that with our industry partners, Wood actually. And then you can see in the bottom right, you can see some of the multi-axial loadings, how pressure varies, pressure is constant. The axial load varies, F as a function of time, and the curvature varies as a function of time. And that comes from a dynamic beam element model called FlexCom, which we've used for global riser dynamic analysis. And then we've used a geometrical model that I'll show you in a moment, which allows us to take the global curvatures as a function of time and convert those into displacements that we can apply to the local axisymmetric FE model. And we've also taken the axial loads, and we can use them with an analytical model to estimate the pressure between the nub in the nub groove contact region. And then the local axisymmetric nub groove model then allows us to quantify the stress tensor as a function of time and the surface shear and relative slip parameters, which we need for defret, for example, or indeed for the explicit wear simulations as a function of time. And then we can come up with total life predictions if we include our crack propagation. This slide shows basically the geometrical analytical link to the finite element model. So this is essentially a geometrical model, which is a little bit complicated, but if you look on the left-hand side, you can see a section through, a longitudinal section through a flexible riser, and you can see the multiple riser nub groove contacts in the pressure armor layer. And what we're saying is this model allows us to convert bending moment, which we get from the global model, dynamic model, into delta applied. So we can actually estimate the relative displacement from essentially the curvature and the angle of rotation theta of a typical section of this riser. We can estimate the delta applied, and the equations are on the right hand side there. So and that then we can then use that in the axisymmetric riser model, and also we can estimate the local pressure, the PA, the local pressure due to the tensile loading on the flexible riser to also apply that to the axisymmetric model, which you can see in the bottom right. And then then we can create these essentially relationships, these analytical relationships essentially between curvature range, which is coming from the dynamic analysis of the flexible riser, and relative slip actually that occurs in the nub groove contact region. And we can do that for a range of different geometries of risers. We've looked at 6, 9, and 11-inch risers in this case, and we can identify the gross slip and partial slip regimes for those. And that allows us to basically essentially generate what are called running condition fretting maps, or CFMs, which allows basically to look at how the life of the riser depends on the curvature, or the curvature range, the dynamic curvature basically coming from the global model. And we can, using our combined initiation and propagation fracture models, we can basically estimate the contributions of initiation and propagation, and we can identify critical regimes of loading, as you can see in this region, around about 0.008 to 0.01 is the critical curvature range, or cyclic curvature range for minimum life. So we can then design against for maximum life, or we can design against critical situations, for example. I'll try and move on then. I think my slide hung. I think my presentation is hung there, not quite. Oh, hang on. Might be able to activate it this way. Okay. So then I said I'd talk a little bit about micromechanics also.
Sorry to interrupt, John. Just giving you a heads up. We're just over 19 minutes now.
Okay, grand. So basically, I'll just talk a little bit about micromechanics before I finish. So it turns out that you may be aware that the fretting strokes and contact weights are typically at the same length scale as metallic grains. So what that means is the cracks are down at the grain level as well. So what we said was, okay, well, let's look at developing micromechanical models which try to see if we can understand about size effects or various microstructure-based effects in fretting. And one of the most, fretting fatigue is well known to be sensitive to contact size. So in particular, as the contact size reduces, we tend to find that the fatigue life increases. So we've looked at, essentially, we've modified our fatigue crack initiation parameters, and there's a well-known parameter called the fatigue-associated parameter, which is quite similar to the Smith-Watson-Topper parameter, and we've applied that in a micromechanical context, as you can see here. And then that allows us, essentially, these are physically based. The intention is to capture the slip band formation idea within the grains. That's the kind of approach. And you can see here a calibration against experimental data, crack initiation data in the bottom right for that type of model. I won't go through the details again, but then we've implemented that to look at statistical size effects in fretting, to look at this contact size effect. So you can see we're looking here at different grain sizes, basically, to see if, and the grain size to the contact width basically means that we can represent essentially different contact sizes. And then what we see from that, if we look at that, we can look at how the contact size basically affects crack initiation. And what that allows us to then do, if you look at the results in the bottom left and the bottom right, you can see that the life gradually, as we reduce the contact size, so the A over D, as that gets smaller, the average life increases. So we're starting to see an effect of the microstructure from these models in terms of trying to capture this contact size effect. Then we've gone on and characterized the microstructure in their basic dual phase ferritic paralytic steels. We've characterized the microstructure in a bit more detail, as you can see here. And then we've developed more complex models, which are basically dual phase models with ferrite and homogenized pearlite, the unit cell model in the top left. We've calibrated those, and you can see in the bottom right that we essentially have 3 fitting parameters here. The critical resolved shear stress, or maybe 4, the critical resolved shear stress for the pearlite and ferrite, and then the C and the D, which are 2 parameters controlling the cyclic plasticity, basically. And all of the other parameters are physically based, essentially, so physical parameters. And then you can see we're matching the microstructure if you look at the grain size distribution in the top right. And then we've looked at this, basically, the so-called contact size effect for 2 different sizes of contacts, where the idea is the stress is kept the same. So the peak pressure and the peak shear are the same. And then I can hopefully run some simulations here which show how the geometrically necessary dislocation evolves. And the GND is a critical strain gradient parameter which can be measured and which controls the hardness of the material, essentially. And what we see is that it's not a very profound effect. It's reasonably subtle, but we do see that the smaller contact size has a much larger, significantly larger density of geometrically necessary dislocations, GNDs. So that's very profound. The effect, you might say, on the damage parameter P, which is this accumulated crystallographic slip, is more subtle, but we can see it is smaller. And if you look at the image on the right-hand side, the table on the right-hand side, sorry, you can see that the lives in general for the smaller contact are in general larger, except for one exception. So there's a statistical effect here as well. They're generally larger than the 60 millimeter case. But this was kind of, if you like, a quick look-see. And then we've also looked at the effect of crystallographic texture between the unprocessed steel, which we've tested, and the cold-drawn steel, which we've also tested. And you can see significant differences in terms of cyclic plasticity for those 2 cases. We've characterized that in terms of our models, and you can see that we're basically applying that then to these micromechanical contact fretting models. And you can see that in general, we're seeing a beneficial effect of the texture, but probably not a dramatically beneficial effect. I think that's my last slide, apart from my conclusions. So then I suppose to sum up, the conclusions are, okay, we've characterized the pressure armor material for flexible risers experimentally in terms of wear and fatigue, fretting wear and fatigue. We've implemented a fretting wear and fatigue framework for realistic riser design. I haven't gone through all the details of the design cases there. We've also looked at micromechanical fretting models to try to rationalize the contact size effect from a modeling perspective. And I suppose some of the conclusions we'd have in terms of those Micromechanics are that, you know, probably it's better to have a larger contact width compared to grain size to resist crack initiation. So we should definitely consider the grain size relative to the contact size. So smaller contacts are beneficial. Smaller grain sizes are obviously beneficial as well in general to resist crack initiation. And the 1:1 texture for BCC materials seem to be beneficial as well. That's my sum total. So I can take questions if that's required, if there's time.
Thank you very much, Sean. We got a question from Alex here, which I'll read out now. So he said, congrats for the presentation. Sean, how do you calibrate the M and C constants for the threatening damage term and the SWT? What's the level of relative displacement you usually expect for the nub groove contact?
Okay, let me see now. Can I stop sharing before
yes, yeah, absolutely.
Can I stop sharing and let me see if I can, where am I? I need to kind of, let me just see if I can come back into the chat or something. Oh, okay, there we go. So can I see the question? How do you calibrate the M and C constants for the, oh, that's a good question. We calibrate those from, well, it's a bit complicated. I'd suggest you look at the papers, but essentially we calibrate them from fretting tests, fretting wear tests. That's the simple answer. But it's a really good question. And it's not difficult, actually. I would say it's not difficult. And it's described in one particular paper, actually. So if you look at the reference in that particular paper, that will describe it. Was there another question there, Sam? The second part of that question?
What's the level of relative displacement you usually expect for the nub groove contact?
Oh, the level of relative displacement. That's a good question. So that was shown on one of the slides. That's a really good question. I'd need let me just have a quick look there.
Yeah, of course.
That was shown on one of the slides. So the kind of level it's actually shown. It's shown here. So let's have a look. So let me see if I can. So we're talking about we're talking around in the particular simulations we did, and what we expect is we're seeing less than about 5 microns. So up to about 5 microns. But again, I think it depends really on the loads. We looked at a bunch of riser design load cases, specific riser design load cases for a particular FPSO, floating production system application, and obviously for particular hydrodynamic conditions.
Yep.
And so, but again, that work is published by Sinead O'Halloran in her PhD and in some papers as well. But what I'm looking at there is down around about 5 microns.
Okay. It's great. Thank you very much. Yeah, great. That was a great question. Good. So I think
that's Alex. Oh yeah, thanks, Alex.
Yes, yeah. So with that, thank you very much, Sean, for your presentation. I think we are a little over time, so I just want to apologize to everyone. Unfortunately, it's pretty difficult to keep these events to time. Sometimes just questions go on and everything. What I've done now for people in the audience is release the attendance certificate link. You can generate your own attendance certificate with that. And now let's close the event out. So again, thank you so much to all of our speakers for presenting with us today. It's been an absolute pleasure to have you here. Always great for me to be sat basically in the front row listening to all these fantastic presentations. Thank you very much to the audience for your interaction, for asking questions. Thank you very much to Optimal Instruments for the support to run this event. As a reminder, please visit our website, surfaceventures.org. You can find recordings of our previous events on there, links to our LinkedIn page where you can find our newsletter released fortnightly, Modern Surface. You can sign up to our mailing list or register for the next event on our website, so you can find out and receive more regular emails from us. Also on LinkedIn. Our next keynote is on the 12th of September with Professor Ben Beek from Micromaterials, so that registration link will be available later. And finally, I would just like to say to all of you there, please do take time to advertise what we do to friends, colleagues, anyone that might be interested. It's always great that we that we continue to grow our community and get more, see more new people attending. It's always great to see everyone interacting in the chat and sharing their perspective and having such great questions. So thank you all very much for your time today. Thank you once again to our speakers. Okay, have a good day, everyone.